Welcome to the video lecture on factoring. Now, factoring can be a tough topic for students, and the best way to get good at factoring is obviously to practice. But we're going to learn a few strategies here to recognize when the best factoring techniques are going to work. So the first technique that we're going to talk about is looking for a greatest common factor, or a GCF. And that's always the very first thing you want to look for before you start factoring. If there is a GCF, you want to pull that out or factor that out first, and then decide if what's left over is something that can be factored even further. But you'll have smaller numbers to work with, and it'll make factoring what's left much easier to do if you pull the GCF out first. So if we take a look at this first example, 125 a cubed z to the fifth plus 60 a to the fourth z to the fourth minus 85 a to the fifth z squared. This has terms that all have a's and all have z's, and the numbers in front, or the coefficients, are all pretty large. So there's a good likelihood that we're going to have a GCF. So let's figure out what that GCF should be. First of all, let's start with the constants, the coefficients. Now, 125, 60, and 85, all three of those end in either a 5 or a 0, and so at the very minimum I know that they're all divisible by 5. So 125 is the same as 5 times 25. 60 is 5 times 12, and you can use a calculator for this if you're not sure, but 85 divided by 5 is 17, so 5 times 17 would give us 85. And 25, 12, and 17 don't have any other common divisors, so the biggest number that all of these have in common would be the 5. So part of my GCF is going to be a factor of 5. Now if we move to our a's, I have an a cubed, an a to the fourth, and an a to the fifth. When we pull something out, we're pulling out the most that we can pull out from any single term. So in this case, that means you're actually going to pull out the smallest power of a that you see in any one of these terms. And in this case, that would be this a cubed. So I can pull out an a cubed. And if I look at my z's, I have a z to the fifth, a z to the fourth, and a z squared. Again, we have to take out the smallest power that they all have. And the smallest power that I see is z squared. So I'm going to factor out a z squared as well. So that is called your GCF, 5a cubed z squared. Then, in parentheses, we're going to write what's left. And what's left should be what you would need to multiply 5a cubed z squared by to get back this original term. Or in other words, this term divided by your GCF. So if I pull out a 5 times what gets me back to 125? That would be just 25, since 5 times 25 is 125. If I pull out all of these a cubes, then all of these are gone, and there aren't any more a's left over. So I don't have any a's, but if I only pull out 2 z's, and I had 5 to start with, then that means I would have 3 z's left, or a z cubed. And you can always check to see if you're factoring correctly, because you can always redistribute, and you should always get back what you started with. So in fact, 5 times 25 is 125. I have a single a cubed, and there's no a's over here, and z squared times z to the third is z to the fifth. So if I were to redistribute, I will get back this first term. So I did that part correctly. Now I'm going to go to the middle term. So 5 times what gives me 60? Well, that was 12. If I pull out 3 a's, but I had 4 to begin with, then I have 1 left over. And if I pull out 2 z's, but I had 4 to begin with, then I will have 2 z's left. And if I double check, 5 times 12 is 60. A cubed times a would give me back a to the fourth, and z squared times z squared gives me back z to the fourth. So that checks out as well. And finally, If I pull out a 5, 5 times what gives me negative 85. I need a negative and I need that 17 back. If I pull out 3 A's but I have 5 to start with, that means I'm going to have 2 A's left over. And if I pull out 2 Z's and I only had 2 Z's to start with, then there's no Z's left. So if I double check, 5 times negative 17 is negative 85. A cubed times a squared is a to the 5th. And z squared times nothing over here stays z squared. So this is my final factored answer. Now when we progress throughout this lecture, sometimes what's left in these parentheses would be something that you could factor further. But in this case, that's not going to be true because my variables are all kind of all across the board and I don't have any more numbers or anything that I can pull out. So we're pretty much done once we get to here, and none of these are like terms, so we're done and ready to put a box around our final answer. So let's try it with this next example. 19p squared y minus 38p squared y cubed. So first thing you want to check for is there a GCF? And I know that there has to be because both of these terms have a p squared and they both have some y's as well. And if you do a little checking on your calculator, 38 is 19 times 2. So 19 also goes into both of these two coefficients. So what's my GCF going to be? Well, I know 19 goes into both of these numbers, so I know I can pull out a 19. They both have exactly the same p's, a p squared, so I can pull out a p squared. And I have a y and a y cubed. For your GCF, you're always using the smaller of the two powers, so I'm going to pull out a y. So in parentheses, we have to write what's left. Now this first term here is kind of tricky and students often make a mistake on this. Don't put nothing right here. Don't put a 0 here or just ignore this because there is a factor left. Remember that when you're factoring out 9p squared y, it's like you're dividing what was originally there by 19p squared y. And when you divide 19p squared y by itself, you get 1, not 0, but 1. So there's a factor of 1 left here. And you need that 1 because you need to be able to multiply by 1 to get back that 19p squared y. Now when I go to the next term and I divide 38 by 19, I'm going to have this 2 left over, and I also need a minus because there was subtraction in between here. So I need a minus 2. If I pull out a p squared, but I only started with a p squared, that means I won't have any p's left. But if I pull out only one y and I had 3 y's to start, then that means I'm going to have 2 y's left, or a y squared. So if I double check here, 19p squared y times a negative 2y squared does give me back negative 38p squared y cubed. So this is my final answer. Now, the next example here is a little bit more maybe confusing to look at, but we're going to do it in exactly the same way. The tricky part on this is that both of these terms have some k's, so there is a GCF. I'm going to be able to pull out some k's, but the tricky part is knowing how many k's to pull out. And what you want to remember is that for a GCF, you always pull out the smaller of the two powers. Now think about that for a moment. If you're dealing with negatives, which number is smaller, negative 2 or negative 4? Well, negative 4 is further to the left on a number line than negative 2 would be. So it's actually smaller than negative 2. So that means the GCF that I'm going to pull out here is k to the negative 4. So in parentheses, what would be left? So how do we figure this out? Well, it's again a little tricky because of the negatives. Think about what it would take to get back to what we started with. K to the negative 4 would have to get multiplied by k raised to some power in order to get to this negative 2. Well, negative 4 plus what gets us back to negative 2? If If I wanted to solve this for that question mark, I could add 4 to both sides. And so the missing power that I need here would be negative 2 plus 4, which is a positive 2. So in other words, I need a k squared here so that when I redistribute and we're multiplying the bases, so we add the powers, negative 4 plus 2 does get me back to that negative 2 power that I started with. So this is correct so far. Now when I go to my second term, I'm going to have this plus 2 left over for sure, and I pulled out k to the negative 4, which is exactly what I started with, so there's no k's left over. So k to the negative 4 times 2 does give me back 2k to the negative 4. So I did factor this correctly, and here would be my final answer. So remember that factoring starts with the GCF, and when you factor something, you're putting parentheses into the problem, unlike FOIL or distributing or multiplying, which is when you're getting rid of the parentheses and multiplying it all out. So here we're going in reverse. It's the reverse of multiplying. We're dividing out a common factor and then writing in parentheses what would be left. Okay, so one more GCF example here. This one's a little different looking, but if you look at this, this is really 2 terms, even though it looks like there's a lot of terms here. We have one whole term here to the left of this subtraction symbol, and one whole term here to the right of the subtraction symbol. And inside those 2 boxes that I have, there's multiplication going on. There's 3p times all of this stuff in parentheses, and 2q times all of this stuff in parentheses. So if we're looking for a GCF, we have to be looking at this box and comparing what they have in common. And you can see that they both have in common this stuff in parentheses. So in this problem, the GCF is actually this stuff in parentheses 1 minus 4p. So if I factor that out or pull that out, then in a second set of parentheses, we have to write what would be left over. So from this first box, if I have pulled this out, then the only thing that's left would be this 3p. And if I go to my second box and I have factored or pulled out this 1 minus 4p, then the only thing that's left is the minus and the 2q. And so this would be our final factored form. So that one's a little different looking. Now what we just did in that last example is actually going to show itself in this next type of factoring technique that we learn. So always, always, always look for a GCF. If you've pulled out your GCF, or if there isn't a GCF, how do you factor from there? Well, the way we're going to figure out what to do next is to count how many terms there are, and that will usually decide for us what factoring technique to use. So if you count however many terms you have, and there are 4 or any even number of terms, then the factoring method we're going to use is called grouping. So for example, in this problem right here, I have 1, 2, 3, 4 terms. And there's no GCF because if I look at all 4 terms together, all 4 of them do not have an M, all 4 of them do not have an N, and all 4 of them do not have a common constant in common. So this does not have a GCF. But because there are exactly 4 terms, we are going to try grouping on this. And grouping is a 2-step process. So the way grouping starts is you take the very first 2 terms and you pull out a GCF just from the first 2 terms. So if I look at m squared and 2m, what do they both have in common that I could pull out? Well, they both have an m in common. So in parentheses, what would be left if I pull out that m? Well, if I pull out an m from an m squared, I'm going to have an m left. And if I pull out an m from 2m, I'm going to have the 2 left. So m times m is m squared, m times 2 is 2m. So this is correctly factored. Now, we're going to do that same thing again, but on the second 2 sets of terms. So if I look at mn plus 2n, what is the GCF of just those two terms? What do they both have in common? They both have an n. So if I pull out an n, then in parentheses, I would be left with an m plus 2. Now, did I pull out a positive n or a negative n? I pulled out a positive n because all the signs here are pluses. So that's step 1 of grouping. Pull out a GCF from the first two terms and write what's left over. Pull out a GCF from the second two terms and write what's left over. And then you have to decide if there's a plus or a minus in between those two sets that you have factored. The second step should be that these two expressions, if you've done this correctly, should match. And if they match, then this becomes just like this last problem that we did up here, where we're going to pull out this quantity in parentheses and write what's left over. So if I notice that m plus 2 matches in both of these, I can pull it out, and in parentheses, if this is gone, the m is left, and if this is gone, the plus n is left. And now I have completely factored this original problem. This is called grouping, and you usually can use grouping successfully when you have 4 terms. It would also work if you had 6 terms or 8 terms potentially, but it has to be an even number of terms. All right, let's try another example. So here's my problem. First thing you want to check is there a GCF? And in this case, there isn't, because I don't have a common number that goes into all 4 terms. An x doesn't go into all 4, and a y doesn't go into all 4. So since there's 4 terms and a GCF didn't work, now I'm going to try grouping instead. So grouping means we take the first 2 terms and we pull out a GCF. Now 6 and 3 are both divisible by 3. So I'm going to pull out a 3, and in parentheses, what would be left? Well, 3 times 2 would get me back to a 6, so this needs to be a 2. And if I pull out this 3 right here, I'm left with the negative and the x. So I have 3 times parentheses 2 minus x. Now I'm going to go to these 2 terms. What do they both have in common? 2y and xy both have a y. So if I pull out a y, then what would be left? Now here we have to be a little bit careful. If I just pull out a positive y, then I would need a y times negative 2 to get me back to this original negative 2y. And a positive y times a positive x would get me back to this positive xy. However, does 2 minus x equal or match negative 2 plus x? No, they don't, because they don't have the right signs. They're exactly opposites of each other. So if these 2 things in parentheses don't match, then grouping's not going to work for you unless you're a little bit clever. So we can fix this problem by, instead of pulling out a positive y, I am going to pull out a negative y. So negative y times what gets me to negative 2y? Just a positive 2. And I would need a negative y times a negative x to get me back to a positive xy. So these signs do check out. This is factored correctly to get me back to the original. But not only that, now these 2 things in parentheses here and here match exactly. So now grouping will work, because I can pull out that 2 minus x, and then in a second set of parentheses, this is gone, and I will be left with 3 minus y. So here's what my final answer would look like. So if grouping doesn't appear to work right away, sometimes there are still ways to make it work by possibly pulling out a negative as well and making your signs match up. And in this next example, we'll see another case where it doesn't look like grouping will work right away, but we can be creative to make it work. So in this example, again, there's no common GCF because there aren't any A's that go into all four terms. Not every term has a b, not every term is divisible by the same constant. So there's no GCF, but there are four terms. So let's try grouping. So if I jump right in, these first two terms, the only thing they have in common is a b, and I'd want to just pull out one b because this term here only has one b in it. So if I pull out a b, then in parentheses, I would have a 4 left, and I'd only have two b's left for this first term. And then for the second term, if I pull out the b, then all I have left is the a squared term. So now if I go to these two terms, they both have a's, and I also noticed that both of these terms are negatives, so it might be handy to pull out the negative as well as the a, because what I have over here was only positive, so I don't want to have any negatives showing up in this second set of parentheses. So if I pull out the negative and the a, then only the 4 is left. And if I pull out the negative and the a from this second term, I would have to have a positive b to the 4th left so that when I redistribute, it'll stay negative. But compare, this does not match this. So grouping isn't going to work because I'm not going to be able to pull out anything in the next step because these two common factors aren't the same. So it looks like grouping failed here, but we can actually get creative and make it work by rearranging the terms slightly. So sometimes grouping won't work if you just jump right in and do the first two and the last two. What I'm going to do instead is rearrange the terms a little bit and see if that helps me be more successful. So let's try switching these two guys around. So I'm going to leave the 4b cubed in front, but I'm going to put the minus 4a next, and then I'm going to put the a squared b term, and then I'm going to leave the minus ab to the 4th on the end. Now this is the same as what I started with because addition is commutative, so you can move terms around like this and not change the problem. But let's see if grouping now works better by turning these terms around. So if I go to the first two terms now, what do they have in common? They both have a 4. So if I pull out a 4, then I would be left with a b cubed, and I would be left with that minus a. Now if I go to the second two terms, what do they both have in common? Well, they both have some a's and they both have some b's. The smallest a that I see is an a to the 1st, so at most I can pull out an a to the 1st. And the smallest b that I see is a b to the 1st, so the most b's that I can pull out is just a single b. So in parentheses, what would be left? For now, let's try just pulling out a positive AB. If my signs aren't the same as the signs over here, then I may need to change this plus to a minus and pull out a negative as well. But let's start with a plus and see what we're left with and cross our fingers and hope it works. So if I pull out an A and a B from a squared b, then all I would have left is a positive a. If I pull out a positive ab from this negative ab to the 4th, I'd have to have a minus left. The a got pulled out, and I pulled out one of the b's, so there's still a b cubed left over. And I just want to double check, a positive ab times a positive a is positive a squared b, and a positive ab times a negative b cubed is a negative ab to the 4th. So I did factor that correctly. Does this match this? Unfortunately, no, because the signs are backwards again. So b cubed minus a is not the same as a minus b cubed. Remember, subtraction is not commutative. Order does matter. So we're really close, but we have to fix the signs. So let's try again. I'm going to pull out instead a minus ab instead of a plus ab. So I would need to multiply negative ab times a negative a to get a positive a squared b back. So that will work. And if I pull out a negative ab from negative ab to the 4th, I would need a positive b cubed. So that negative ab times positive b cubed is negative ab to the 4th. So now do these match? So be careful here. They don't look quite the same, but remember that negative a plus b cubed is the same as b cubed minus a. If I just switch the order here over that addition. Addition is commutative, so I can swap these two around, and I do get exactly the same expression here. So this is really the same as negative ab times b cubed minus a. So by pulling out that negative, I did get these two guys to match. So now that they finally match, I can pull it out, and in a second set of parentheses, these are both gone, and I will be left with my 4 and my minus ab. And so after all of that work, here we finally have our factored answer. So if grouping doesn't appear to work right away because the stuff in parentheses doesn't match, again, there are ways to get around that. Sometimes you have to pull out a negative to make the signs match, or sometimes you might need to rearrange two terms. Like here I swapped the second and the third term, and that will end up making the stuff in parentheses match. So grouping doesn't always fail right away on the first term. You may need to rearrange terms or pull out some negatives to get it to work. All right, so let's recap what we know so far. If you are being asked to factor a polynomial, what that means is you're trying to pull out some factors and rewrite it in its factored form, which means in parentheses. So you're putting parentheses into the problem and having it be something times something else. When you're going to factor, the very first thing you always want to check for first is there a GCF? If there is, pull it out right away. After you've pulled out a GCF, or if there isn't even a GCF, the next thing you want to do is count how many terms are in your polynomial. If there are 4 terms, then we try grouping. If there are 3 terms, then we're going to try reverse FOIL. And this is kind of a tricky process here. So we're going to start easy and work our way harder. So if there are 3 terms, there is going to be this method called reverse FOIL that we're going to use to factor our trinomial. If you have 3 terms in a polynomial, that's called a trinomial. So in the simplest case, that trinomial would have a leading coefficient of 1. So that's what this first example is. This leading coefficient is a 1 here. When that happens, so when you have 3 terms like this and the leading coefficient is 1, this is much, much, much easier to factor. And the way that we're going to factor it is we're going to think about what it would take to FOIL out and get back this answer. So think about reverse FOIL. FOIL is a binomial times a binomial. So it's 2 things in parentheses multiplied together. So in this kind of a problem, when you have these 3 terms here, in order to get the x squared in the front, the only way we can multiply 2 things and get x squared is if we have an x times an x. To get the constant on the end, that comes from the last term times the last term. Now there's several ways to get 12. 3 times 4, 2 times 6, 1 times 12. But remember in FOIL, it's not just the first and the last. You also have to consider the outers and the inners. So these outers and inners, actually these are the outers and these are the inners, that is where the middle term comes from. So if we want to figure out what number should go here and here, not only do we need 2 numbers that multiply to 12, but we also need those 2 numbers to also add or subtract to this 7x in the middle. And if you think about the factors of 12, 3 times 4, that multiplies to 12, but 3 plus 4 is also 7. So let's try a 3 and a 4. And if I make them both plus, then I get a positive 12 on the end, and 3 times x for the inners would be a positive 3x, and 4 times x would be a positive 4x, and so the middle terms will be 7x. So x plus 3 times x plus 4, if I were to FOIL it out, is going to give me the x squared in front that I want. I'm going to get a 4x for the outers. I'm going to get a 3x for the inners, and a 3 times 4, or 12, for the last term. And when I combine these two middle terms, I do get back x squared plus 7x plus 12. So that means this is the correct factorization of x squared plus 7x plus 12, because not only do I get x squared and 12, but I also get the right middle term as well. So that was a lot of talking for a very simple process here for these examples where the leading coefficient is 1. So here's what you do again. You're going to find two numbers that multiply to this constant term on the end, the last term, and those two numbers also have to add or subtract to the middle coefficient. Okay, so let's try that again on this example. First of all, there's no GCF, and this is a trinomial. It has 3 terms, so that's how I know that I'm going to try reverse FOIL. So reverse FOIL is where we're going to put down 2 sets of parentheses, and we're basically trying to fill in these 4 spaces. Because the leading coefficient is a 1, there's only going to be one way to get x squared, and that's x times x. To get the last term on the end, you have to think of factors of 28. So we're looking for two numbers that multiply to 28, but at the same time, those two numbers also have to either add or subtract to this middle coefficient of -3. So let's think about the factors of 28. 28 is 1 times 28, it's 2 times 14, or it's 4 times 7. And 4 and 7 have a difference of 3, so that looks like a potential candidate for what numbers I should use here and here. So let's put 4 here and 7 here. And now we have to worry about the signs. In the middle, I'm going to get a 4x from these two middle terms, and I'm going to get a 7x from these two outer terms. If I want to get a -3, then I need the 7 to be negative, so I need to put a minus sign here, and I need the 4 to be plus, so I'm going to put a plus sign here, and that way a positive 4x and a minus 7x will give me a -3x on the inside. And also double check your sign of your constant term. A positive 4 times a minus 7 does give me a -28. So my two factors that work are x plus 4 times x minus 7. And remember, you can always refoil this out, and you should be getting back what you started with. If you don't, then something's wrong, your signs are off, your constants are off, and you need to rework the problem. Okay, so this is the easy case of reverse FOIL because the leading coefficient is 1, and so in the front you'll always just have that x times that x, and you only need to worry about the constant term on the end and look for two numbers that multiply to that constant and either add or subtract to that middle term. So now we're going to move to the harder case, and this is hard because there are often many combinations that you have to check to make this work. So this is going to be the case when the leading coefficient is not a 1. So we're still going to do reverse FOIL, but we're going to have to do a lot of trial and error until we find the right combination of factors that not only gives us the right leading term and the right constant term, but the combination of those also has to give us the right middle term. So these are not easy. There's a lot of trial and error. So be prepared to be checking lots of scenarios until you find the combination that works. So how do we do this? Well, don't forget, before you jump right in, always, always, always check for a GCF. So if I look at this problem, unfortunately there isn't one because 6, 5, and 14 do not have any common factors. So I can ignore the GCF, and now I can jump right into my reverse FOIL. So just like before, we're still using two sets of parentheses. That's what reverse FOIL means. And you're still going to be filling in these 4 spots. But now the number of combinations and possibilities has increased because there's not just one way to get 6x squared. Yes, you need an x times an x, but you could do 2 times 3 to get 6, or you could do 1 times 6 to get 6. So there's a couple of combinations for what coefficients should go in front of those x's. So that's why this is going to be a harder kind of problem to solve. There's also several ways to get 14 as well. 1 times 14 or 2 times 7. And some combination of all of that has to give us a -5 in the middle. So when there's all these possible combinations, you're going to have to work through the possibilities. And so what I like to do is fix one possibility and work through all the potential outcomes of that, and then see if any of those work, and if they don't, then I try a different possible combination. So what I mean by that is, let's start with our 6x squared. There's more than one way to get 6. You can do 2 times 3, or you could do 6 times 1. So I'm going to guess that it's going to be 2 times 3. So I'm going to fix that in place. Now once I fix that, then I'm going to list all the possible ways to get 14. Now you can get 14 with a 2 times a 7, but order matters here because we're going to get different middle terms based on where I position the 2 and the 7. So not only do I have to consider putting the 2 here and the 7 here, but I also could possibly get a different answer if I put the 7 first and then the 2. So we need to put down both of those possibilities and check to see which one of them works. Now that's not the only way to get 14. I could also get it by doing 1 times 14, or I might get a different solution if I do 14 times 1. So those are all the ways to get 14, with one potential way to get the 6. So I'm going to work through each of these and see if any of them give me this -5 in the middle. So how do I decide which one works? Well, we run through our list, and what we're checking is the middle term only. I don't need to worry about 2 times 3 because I already know that's going to give me 6. And I don't need to worry about these two numbers multiplying because I already know they're going to give me the 14. The only thing that I'm checking is what the middle term will be, and I want it to be a -5. So if I check my first combination, which would be this 2 and this 7, I'm going to check the inner times the inner and the outer times the outer. 2 times 3x would give me 6x, and 2x times 7 would give me 14x. Now, can I add or subtract 14 and 6 and get a 5 out of that? No. If I add these, I'll get a 20. If I subtract them, I'd get an 8. So I'm not going to get a 5. So this option didn't work. Didn't give me the right middle term. So that means I move down my list, and I'm going to cross off the 2 and the 7, and I'm going to move to my next option, putting the 7 here and putting the 2 here. So if I do this middle term times this middle term, inner times inner, 7 times 3x would be a 21x, and 2x times 2 would be 4x. Can I add or subtract 21 and 4 and get a 5? No. So this option doesn't work either. So I cross it off and I move down my list, and now I'm going to use the 1 here and the 14 here. And we're doing inner times inner. So 1 times 3x is 3x. 2x times 14 would be 28x. 28 and 3 will not add or subtract to a 5. So that option doesn't work either. So I move down the list, and now I'm going to try 14 here and 1 here. So what's 14 times 3? So if I do a little scratch work here, that's going to be 42x. And 2x times 1 is 2x. 42 and 2 are not going to give me a 5. So that didn't work either. So none of these worked. What does that mean? Does that mean that this doesn't factor? Unfortunately, no, because remember what we did at the very beginning. We assumed that to get 6x squared, it had to be 2x times 3x. But that's not the only possibility. Remember, you can also get 6x squared by doing 6x times a 1x. And so we have to go back and start all over again, and we have to try that new combination. So that's why this is trial and error. I'm going to erase all of these. And unfortunately, we now need to start from scratch. So instead of getting 6x squared with a 2x times a 3x, let's try a 6x times a 1x, or just an x. And once I've fixed those, I still have to list every possible combination to get the 14. So either 2 times 7, or I could get a different middle term if I put the 7 here and the 2 here. Or it could be 1 and 14, or it could be 14 and 1. And so we go back and we try the top choice here, and we're going to do inner times inner. 2 times x would be 2x. And then we're going to do outer times outer. 6x times 7 is 42x. 2 and 42 do not give me a -5. So that option doesn't work. So I move down my list. Now I'm going to try 7 and 2. So 7 times x in the middle would give me 7x, and 6x times 2 gives me a 12x. And finally, that will give me a 5 if I subtract. Now I want a -5, so I need the 12 to be negative, and the 12 comes from this 6x, which I've already said is positive, times this 2. So in order to make this be a -12, I need this to be a -2. And I want the 7x to be positive, so I want to put a plus sign in front of the 7. So it looks like if I do 6x plus 7 times x minus 2, I know that I'll get a -5x in the front. I know that I'll get a 6x squared out front, and a positive 7 times a -2 does give me a -14 as well. So we finally figured out the two factors of this trinomial. So reverse FOIL, when the leading coefficient is not a 1, is very time consuming because you have to check every possibility of not only the front number but also the back number. And so you often have to go through several different checks until you find the case that works. All right, let's try this example here. So first thing when I look at this should look a little bit different than the last problem, because not only do we have big coefficients, but we also have bigger powers on our variable. And so when you see something like that, that's usually a clue that there's probably a GCF involved, if you've got big coefficients and big powers. And in this case, there is, because if they all have some z's, I know that at the very minimum, I should be able to pull out a z cubed. And if I look at 32, 20, and 12, I know that all three of those numbers are divisible by 4. They're divisible by 2, but I want to pull out the biggest integer that goes into all of them, and that would be a 4. So my GCF, my greatest common factor, should be 4z cubed. So what would be left if I divide all of these by 4z cubed? Well, 4 times 8 would be that 32. And if I pull out 3 z's, then I should have a z squared left to get me back that z to the 5th. If I pull out a 4z cubed from the middle term, I need a minus and a 5 to get the -20. And I pulled out 3 z's, so I have 1 z left. And then on the end, a minus 12z cubed, I need a minus and a 3. And I pulled out all the z's, so there aren't any z's left. So that means here's my GCF pulled out. Now that doesn't mean we're done factoring, because what's left here could potentially factor some more. And how many terms are left? 1, 2, 3. So this is a trinomial, and that means this could potentially factor using this reverse FOIL technique. So I'm going to put 2 sets of parentheses down, and what we have to figure out here is what could we multiply in the front to get an 8z squared, and what do we have to multiply in the back to get that 3, and what combination do we have to have so that the middle term ends up being a negative 5. So there's more than one way to get 8, but I do know I need a z times a z to get z squared. And this could either be 2 times 4 or 8 times 1, depending on the combination that's going to work. So I'm going to consider those possibilities in a moment, but let's jump to the 3. The 3, there's only one way to multiply to 3, 3 times 1. So since there's only one way to do 3, that's the one I'm going to fix. And I'm going to put the 3 here and the 1 here. And that means when I go to my first spot, this is where I'm going to list all the potential ways to get 8 in both potential orders. So what I mean by that is if I put 2 times 4, that will get me 8z squared. But I may have a different middle term if I put the 4 first and then the 2. So you have to consider both alternatives. We could also do 1 times 8 or 8 times 1, and that would give me 2 potential solutions as well. So how do I know which one's going to work? Well, we always have to check the inners and the outers, okay? So if I do this first case, the 2 and then the 4, the inners would be 3 times 4z, which is going to be a 12z, and a 2 times 1, or 2z times 1, which is a 2z. Does a 12 and a 2 give me a 5 in the middle? No. So this option doesn't work. So I move on to the next potential case. And I'm going to do 4 and 2. So inner times inner would be this 3 times this 2z. 3 times 2z would give me inner term of 6z. And 4z times 1 would give me a 4z. And 6 and 4 can't give me a 5 either. So that choice doesn't work. So I cross it off and I move down the list to the next possibility, which would be a 1 and then an 8. So 3 times 8 is 24z, and 1z times 1 would be 1z. 24 and 1 is not going to give me a 5, so that doesn't work either. So I cross it off and I go to the last option, which was the 8 times the 1. So inner times inner would be this 3 times this 1z, which is 3z. And 8z times 1 would be 8z. That does give me a 5. I want it to be a minus 5, so I want the 8 to be negative. Now the 8z comes from this 8 and this z out front, which I've already written here as positive. But I do have control over the sign of this 1. So if I make this 1 negative, that'll give me a negative 8z when I do outer times outer. And I want the 3z term to be plus, so I want to put a plus in front of that 3. So it looks like if I do 8z plus 3 times 1z, or just z, minus 1, that should work. Now, a couple of things. I'm not quite done, because remember, this problem from the very beginning had a GCF, so don't forget about that 4z cubed that we pulled out from the start. That is still in your final answer. So I want to make sure that I bring that down, and this would be what my final factored form would look like. One other comment about all of these problems is, does it matter which of these two factors you put first? And the answer is no. So this answer is also the same as 4z cubed times z minus 1 times 8z plus 3. The order of the factors doesn't matter, just the numbers inside and what signs they have is what matters. So both of these two answers would be correct. All right, so reverse FOIL is the toughest method that we have when we're trying to factor because there is so much trial and error involved. So be very patient, and I promise it will get easier with practice as well. So let's run down through our list here of how to factor one more time here. Number one, first and foremost, check for a GCF. After you've checked for a GCF and either pulled it out or there wasn't one, then you count how many terms you have. If there are 4 terms, then you try grouping. If there are 3 terms, then you use reverse FOIL. If there are 2 terms, then we're going to have a special pattern called a difference of squares, which might work if your polynomial fits that pattern. Now, we saw a difference of squares when we were doing our lecture on polynomials and we were multiplying. So this is that same pattern, but now we're going to use it in reverse so that we can factor. So difference of squares is actually nice. It's a nice problem to do. It's really quick factoring to do because it's super easy to figure out how to factor because it has this nice special form. So here's what difference of squares has to look like. It has to be some quantity squared minus some quantity squared. If it is, then this will factor into basically the square root, if you will, of this first term. So that's what the box is. And then the square root of this second term. That's what this triangle is. And your terms inside have to have alternate signs. So one of these factors should be plus and one of these factors should be minus. They have to have opposite signs so that there's no middle term when we FOIL it all out. So for example, if I have 4x squared minus 9y squared, this is a difference of squares because it's a quantity squared minus a quantity squared. And so right away, I know that this is going to factor into 2 sets of parentheses. In the first spot here and here, we're basically kind of taking the square root of 4x squared, or what times itself would give you a 4x squared. Well, that would have to be a 2x times a 2x. And what times itself would give you a 9y squared, a 3y, and a 3y. And in this difference of squares pattern, the first factor, one of these is plus and one of these is minus. You could also write this as 2x minus 3y and 2x plus 3y. It doesn't matter which one's plus and which one's minus as long as you have one of each. So this would be my final factored form. And I just want to point out the reason why this works is we know we're going to get 4x squared when we multiply the first times the first. And we know we're going to get negative 9y squared when we do last times last. But when you check the inners, you get a negative 6xy. And when you check the outers, you get a negative 6xy, a positive 6xy. And because these signs are opposites, these middle terms cancel out. And that's why there's no middle term in the original polynomial. So you have to have alternate signs. All right, so let's try this again on x to the 4th minus 1. So is this a difference of squares pattern? Is it a square minus a square? And the answer is yes, because anything raised to an even power is something squared. So this is an x to the 4th, and that means this can be broken down into something times itself. Because if you do an x squared times an x squared, you will get an x to the 4th back. The square root of x to the 4th is x squared. What times itself gives you 1? Well, that's just 1 and 1. And to be this difference of squares pattern, one of these should be plus and one of these factors should be minus. So I'll make this one plus and this one minus. Now, am I done? Not quite. When you have these higher degree terms, if you have something in your problem that is already bigger than an x squared to start with, be on the lookout, because a lot of times when there's higher powers, like this is an x to the fourth, a lot of times those problems will factor more than once. So you're not done after you factor it once. Sometimes what's left will factor some more. And that's the case here, because this second factor right here is another difference of squares pattern, because it's something squared minus something squared. And that means this will factor again. What times itself gives me x squared? X and x. What times itself gives me 1? 1 and 1. Make one of these plus and one of these minus so that we don't get any middle term. And so x squared minus 1 factors into x plus 1 and x minus 1. For your final answer, don't forget to bring this guy down. It's still there. So your final answer in this problem should actually have 3 factors. Now, a question that I often get is, well, why can't I factor x squared plus 1? Why isn't that just x plus 1 times x plus 1? And the reason why it's not is because when you FOIL out x plus 1 times x plus 1, you do get an x squared, but you also get a plus x, and a plus 1. And when you combine those middle terms, this is actually x squared plus 2x plus 1. So it doesn't factor into x plus 1 times x plus 1 because the original polynomial did not have a middle term, but that's what you get. You do get a middle term when you multiply x plus 1 times x plus 1. So this is actually wrong, and you can't factor a sum of 2 squares. You can only factor a difference of 2 squares. So it has to be subtraction when you're doing these problems. Okay, that's really, really important. So you have to have subtraction. So what if I told you that I wanted you to factor x squared plus 4? Could you factor that? In this case, no, there's no GCF, and it is 2 squares, but it's not a difference of 2 squares. So this is what we would call prime. If something doesn't factor, then it's called prime. So just be on the lookout. X squared plus 4 does not factor because it's a sum of squares. But something like x squared minus 4 would factor because it's a difference of squares. So this would be x and x, 2 and 2, a plus and a minus. So whether it's a plus or a minus really makes a big difference. Okay, we're going to finish off today with just some mixed problems. So these are all polynomials that have all different things going on. And so we have to kind of work through our checklist of factoring to decide which factoring technique should we use. So in this first problem, I have 5x to the fourth minus 80. Now right away you should notice that this only has 2 terms. So if this is going to factor, the only way that it's going to factor is if this is a difference of squares. And 5 is not a perfect square, and 80 is not a perfect square. So it doesn't seem likely that this is going to factor using that difference of squares pattern. But it does factor because we are overlooking the fact that there is a GCF in this problem. So don't forget, the very first thing you should always be checking for is there a GCF? And this one has one because 5 goes into 80. So if I pull out a 5, then in parentheses, I'll be left with that x to the fourth, and 5 times 16 is 80. So I would be left with a minus 16. Now, just because I pulled out a GCF doesn't mean I'm done. Now you have to look at what's left and see if that factors some more. And this time, again, I only have 2 terms here, but I have a perfect square because it's an even power, and I have a perfect square because 16 is 4 squared. So these 2 terms here are a difference of squares, so I can factor them some more. Now I don't want to lose my 5, so write your 5, bring that down, but then we can set up our 2 sets of parentheses, and it's going to be an x squared times an x squared to get me that x to the 4th, and I need a 4 times a 4 to get me that 16. One of these is plus, and one of these is minus. Now are we done? No. Remember, when you have these higher powered problems, especially x to the 4ths or higher, they're often going to factor multiple times. So this isn't done because this is now a difference of squares as well. So it's going to factor some more. So bring down your 5, bring down your x squared plus 4. Remember, that one doesn't factor anymore because it's a sum of squares, not a difference. But then this last one will break down even more. 2 sets of parentheses, and I would need an x and an x to get x squared, and a 2 and a 2 to get the 4, make one of them plus and one of them minus, and finally, here is our factored answer. Okay? All right, next example. Again, this has 2 terms as well. So we're on the lookout for that difference of squares pattern. But right away, I know I have a problem because this isn't a difference, it's a sum. So we might think that this is prime, but it's not because there's a GCF. Anytime you can pull out a GCF, you need to factor it out. 4 goes into 4 and 4 goes into 16. So if I pull out a 4, I'm left with x squared plus 4. Now don't stop here, double check. Does what's left factor anymore? And in this case, no, it doesn't because it's a sum of squares, not a difference of squares. So this is where we have to stop. We can't factor any further. Okay, next example, 12a squared plus 17ab plus 6b squared. So is there a GCF on this problem? Unfortunately, no, because 17 is prime, so there's not going to be any constant that goes into all 3 terms. There aren't a's in all 3 terms, and there aren't b's in all 3 terms, so we don't have any GCFs to pull out. So we rule that out. We count how many terms we have. We've got 1, 2, 3 terms. So if this is going to factor, it's got to be via reverse FOIL. And unfortunately, the leading coefficient here is a 12, not a 1. So this is that harder case. This is that trial and error case. So we're going to have a little bit of work ahead of us. So what I'm going to do is 2 sets of parentheses. In the first positions, I need 2 things that multiply to a 12a squared. Well, I know I have to have a times a. But there's multiple ways to get 12. There's 2 times 6, there's 3 times 4, there's 1 times 12. So there's lots of possibilities there. So let me hold off on writing those down for a minute. Now let's look at the constants over here on the ends. How can I multiply to get a 6b squared? Well, I know that I need a b and a b, and there's a couple of ways to get 6, 2 times 3 or 1 times 6. So this is the hard case because you have to sort of fix one of these, either fix an option for the 12 and list all the ways to get 6, or fix one way to get 6 and list all the ways to get 12. Since there are fewer ways to get 6, that's the one that I'm going to fix, and I'm going to make a guess, and I'm going to hope that it's 2 times 3. If, after I do this for all the ways to get 12, this doesn't work and I can't get 17 in the middle, then I would have to start all over again and change the 2 and the 3 to a 1 and a 6, and then work through my list again to figure out how to get that 12 in front and get a 17 in the middle. But let's cross our fingers and hope that 2 and 3 are the right choices here. So now we have to fill in all the ways to multiply to 12, and we have to do it in both orders because the 2 different orders could result in 2 different middle terms. So 12 could be 3 times 4 or 4 times 3, 2 times 6 or 6 times 2, 1 times 12 or 12 times 1. So how do we decide which one works? Well, I'm going to circle the top 2 numbers, and then I'm going to do the inner time the inner. 2b times 4a would give me an 8ab in the middle. Now I'm going to do last times last. 3a times 3b is 9ab. Whoa, I got really lucky here because 8 plus 9 does give me 17. And I want a positive 17. So I want both of these to be plus. So I need both of these signs to be plus. So we got super lucky because we got the answer on our first try with our first guess. So it looks like this factors into 3a plus 2b times 4a plus 3b. And you can always refoil this out to double check that you do indeed get all three of these terms with the correct signs. Okay? All right, our last example. 3x to the 6th minus 14x cubed plus 8. So first off, is there a GCF? No, because 3 doesn't go into 14 or 8. And then I don't have x's everywhere, so I can't pull out an x from all three terms. So this does not have a GCF. And there are three terms, 1, 2, 3. So this must be a reverse FOIL kind of problem. So we're going to set up two sets of parentheses. And in this first position, I need to think of how I can multiply two things together to end up with a 3x to the 6th. And notice that in the middle, my middle term here has an x to the 3rd for the variable. So think about what that implies. That implies that you have to have an x cubed times an x cubed so that your middle term will also have an x cubed in it. And there's only one way to multiply to 3. 3 times 1. So I'm going to go ahead and fix the 3 times the 1. Then over here, there's multiple ways to get 8. And I have to consider all possibilities, both orders, because I could end up with different middle terms. So I could do 2 times 4. I could do 4 times 2. I could do 8 times 1. Or 1 times 8. And what I'm checking, I'm going to do the top pair first, is the inner times the inner. So 2 times a 1x cubed would be 2x cubed. And then I'm going to do the outer times the outer. 3x cubed times 4 would be 12x cubed. Can I get a minus 14 out of that? Yes. If I make both of these negative, so I have to make this negative and this negative, this will add to a negative 14x cubed. And I also want you to double check that 8 on the end because you need to have the right sign on that 8. And we will, because a minus 2 times a minus 4 does give me a plus 8 on the end. So this actually will work. And we get 3x cubed minus 2 times 1x cubed, or just x cubed, minus 4. And just a quick check, because this was a problem with a much higher power. This had an x to the 6th in it. So just double check that both of these don't factor any further. And potentially the only way they could factor is if one of these had been a difference of squares, which is not going to happen here because an x cubed is not a perfect square since it's an odd power. So it looks like we're done. All right, so that concludes our lecture on factoring. Remember to always check for a GCF and then count how many terms there are. If there are 4 terms, use grouping. If there are 3 terms, try reverse FOIL. And if there are 2 terms, try a difference of squares pattern. And if none of those work, then we would say that the polynomial is prime and it does not factor. Good luck.